And today we finally get to convolutional neural networks. After talking about all this multinomial classification and all that messy stuff and introducing Keras, that was an important thing of what was in the lecture on Wednesday. And I can't emphasize how nice Keras is because one of the more popular and more powerful software tools is called TensorFlow. It is a pain to program in TensorFlow. I do not enjoy having to go and fight with it's really weird. It uses all this weird stuff with the dictionaries in Python, and it's really weird. Keras is very straightforward. It's much more scikit-learn-like, so it's very helpful. And so when we move into these convolutional neural networks, I want to go ahead and revisit what a convolution is, just what we introduced before when we were talking about edge detection, you'll remember. And it's basically a way where you have some sort of what's called a kernel, and it's kind of like a mask, and you like swing this kernel across the image and look at different places, and the mask is kind of like weights. Each one of the values in here is kind of like a weight for each individual pixel. And you slide, is kind of like a slide in window search too, where you slide this kernel across and you multiply each one of the weights in the kernel times the pixel value, and you sum them all together to get the pixel values in the convolved image. Okay? And we talked about the Sobel convolutions, where we were looking for either horizontal lines or vertical lines. We also talked about the Gaussian blur, when we sort of got rid of, sort of smoothed out the image before we looked at edge filtering. And when we do some looking at this selective search, there'll be some more types of Gaussian type things we're going to look at. So this idea of convolution is pretty old in terms of image processing. There's all sorts of different ones, and you can develop different features with these convolutions. Okay, and that's essentially what we did before, using them to get edges. A little bit more details in terms of these convolutions. It doesn't play so much of a role when you're just calculating features, but in convolutional neural networks, these things become parameters and ways you can decide on how to do things in your network. The first thing I'll talk about here in this first row is padding. And essentially, if here I have a 3x3 kernel, that shaded area is 3x3, and I have a 4x4 image. And so when I put the 3x3 piece in there and shift it over, I can only do two in every row, and every column only has two unique places to put that kernel. And so I had a 4x4 image, and I end up with a 2x2 convolution, which may or may not be an issue. I mean, usually it makes more sense for the convolution to be the same size as the original image, especially if you're trying to compare them or lay them over top of each other. And so we can use zero padding, where in this case I put one layer of zeros around the outside of the image, and it's one layer because it's a 3x3 kernel. Had it been a 5x5 kernel, to do this half padding, I would need 2 layers around there. So that the idea is that when you place the kernel all the way on the edge, that the middle of the kernel is on the edge of the original image. And that way, as you move it along, here it's a 1, 2, 3, 4. This is a 5x5 image with a 3x3 kernel, and it results with a 5x5 image. Okay? Now, that's half padding, sometimes called same padding, because you end up with the same size as what you had before and after the convolution. You can do full padding, which it is called full padding in Keras. Basically, these are the words that often people associate with them, and these are the words in Keras. If you want to put the padding, use valid for that, same here, or full here. And then the full padding makes sure that not the center of the image is the first point in the pixel, but the edge of the kernel. You can see, the kernel moves all the way off, and there's only one pixel in the kernel that's on the image. And that's full padding, so you get it actually expands the size of the image. It's a little bit bigger using full padding than the original one. Okay? Half padding is probably the most common one. Then, another thing that you can do, all of these here are moving the kernel by 1 pixel to the left, 1 pixel in rows and 1 pixel in columns. I don't have to do that. I can skip pixels. This is a 2 by 2 stride that I jump 2 rows and I jump 2 columns every time. And you can see, I'm basically not covering every piece. And we did this with a sliding window search. If you shifted every pixel, it would be a ridiculous amount of things, so you jumped every so many pixels to make it, be faster. In this case, it's faster too, in the sense that I end up with a smaller convolution, but it's still covering the entire image. With that half padding, I'm still covering all the way out to the edges, but it's a smaller image because I'm skipping some parts. Okay? And of course, all this, like anything else, you can play with these, you can mess them around, you can do all sorts of different things. In the end, it probably doesn't make all that much difference if you do 2 by 2 strides or 1 by 1 strides. It's one of those things, it's just a tunable parameter. You mess around and sometimes you might find that one works better than the other. Okay? All of these use a 3 by 3 kernel. All these examples, that gray shaded area is 3 kernels by 3 pixels by 3 pixels. Of course, you can have 5 by 5. You can have whatever. Usually, we choose it to be an odd number so that there is a center pixel in the kernel. So that's convolutions in general. Okay, just sort of a review of them. And I'm going to show you here how we can use convolutions in order to create features. And it's sort of leading us towards what's going to be in a convolutional neural network. So let's take a situation where I've got this 9 by 9 image and I'm trying to decide, is this a square in the image or is it not a square? Okay, and so intuitively you could say, well, if it's a square, there should be a line, a white line at the top, the bottom, the left, and the right. Okay, here there's one on the left and right, but not the top and the bottom. Here in this circle thing is not really any straight lines. So if I look for a straight line at the top, bottom, left, and right, that should tell me whether it's a square or not. Okay, so I could go ahead and apply a Sobel X and a Sobel Y convolution. Okay, and get in the terminology of convolutional neural networks, this is what's called a feature map. Okay, so it's not the original image, but it's something that has some sort of features built out of it. And you can see, putting the Sobel X, I see, yes, there's lines on the left and right. There's lines on the left and right. There's kind of, sort of, but not really lines on the left and right. In the same way, it does the same thing for the top and the bottom. Here, there's not really a line on the top and the bottom, is there? Okay, so we can start to see that the information in these features is more helpful than just the overall image. Just like Ben was in here before saying how we need to simplify the things so that we can identify what we're looking for. Okay, now the idea that we're starting off with is, what is is there a line on the left and is there a line on the right? Okay, and right now I've got this 9 by 9 image that still has quite a lot of resolution that I don't really need. I want to know what's happening on the left, what's happening on the right. Okay, so one thing we can do is this idea of pooling. And what pooling does is it takes a section of the image. In this case, I did 3 by 3 pooling. So I took a region of 3 by 3 pixels, and in this case, I used max pooling. You can use average pooling. You can do all sorts of different things, log pool, who knows? There's all sorts of different pooling that you can do. But basically what I said is, well, of the 9 pixels in this region, what is the brightest pixel? Okay, and that's this guy right here. And so I go ahead and make the entire area there be that color or that value. Because remember, the colors just represent a number. Okay, so we're going to make the resulting space, this pixel right here, be the maximum color out of that 3 by 3 region. In that 3 by 3 region, the white is the brightest color. Okay, in that 3 by 3 region, all of them are gray, so it's just going to be gray, etc. And so we now build an image here. So these are now, this turns into that. It went from 9 by 9 to be 3 by 3. Okay, so I can sort of localize. I want to do this max pooling so that I get, the size of what I'm looking for. Now I've got stuff on the left, stuff on the right, stuff in the middle. Okay, and when I've done the max pooling on the Y one, I've got stuff on the top, stuff in the middle, stuff on the bottom. And so we can see now, at least for this image, it's super bright. It's as bright as can be on the right and the left. There's definitely lines on the left and right. Okay, here it's just sort of so-so. It's actually kind of dark in some places. There's not really lines on the left and the right. Okay, here on the right side, yeah, it's white, very, very bright white. Here it's pretty bright. Okay, certainly that pixel is bright. The others are relatively bright. Okay, and then the same thing here. At least for this guy here, there's definitely nothing on the top and the bottom. It's not very bright. It's not very bright. It's very bright there. It's pretty bright there. So now you can see how we boiled it down. We took the overall 9x9 image. We applied got some features out of it by applying a convolution, and then pooled together things so I can look at particular locations that I'm interested in. Okay, so if you look at the numbers, and I have code, there's code that I uploaded that actually does this, and you can look at the numbers. Here, this is a normal uint8 image, so black is 0 and white is 255. And then applying the Sobel filter, as it turns out, it's it's -1, -2, 0, +1 or +2. So you can multiply the 255 by 2, and then you could either subtract or add depending on where the signs are, so it could end up being 4 times larger than the pixel value. So 4 times 255 is 1020. So that's the largest pixel value I'm having in these feature maps. Okay, and so this bright white represents 1020. Okay, now what we could do in order to identify the regions of the image that we're interested in. We're interested in the left part of the image, we're interested in the right part of the image, we're interested in the top and the bottom, and we're not interested in the middle in those places. So we can say, well, we want to have a weight of 1 for the places I'm interested in, and a weight of 0 the things that I'm not interested in, and do this element-wise multiplication of the color of that pixel in the pool times that weight, and then sum them all together, and these are the numbers you get. And clearly the square has a much larger value than the other two. Worked pretty well. Okay? Now, in the end, we want to end up with some sort of a classification that says yes for square and no for the others. Okay? So one thing we could do is we could go ahead and subtract 900 from this to make the square be positive and the others be negative. And the reason I do that is so that if I want to go ahead and apply the logistic sigmoid, you'll notice that when x is negative, that makes e to the positive value. That's going to be big. The numerator is big. That makes it be close to 0. When x is negative, when x is positive, e to the negative positive number is going to be a very number close to 0. When it's close to 0, then I get 1 over 1, and I get 1. Okay, so I've changed by subtracting the bias here to make things that I want to be squares be positive and things I don't want to be squares to be negative. Plugging these values now into my logistic sigmoid give me a value of 1 for the square and 0 for the ones that are not a square. This is pretty successful. Works pretty nice. Okay, and it's pretty similar. It's basically the same thing of neural networks like I've already shown you. We produce the features. The features are essentially all of the different pixel values in the pools, and we feed these pools into a neural network, got the weights, and then an activation function. Okay, so it's not really any different than what I've shown you before, but I'm sort of packaging it in a different way that's going to lead us to these convolutional neural networks. Okay, so let's organize this process in a little bit different way. We're starting off with our original image, and we're going to apply 2 convolutions, okay? The Sobel X and the Sobel Y. And those 2 convolutions are going to result in these feature maps. So the first thing I'm going to do is a convolution. In this case, I happen to do 2 convolutions, okay? Then what I do is I go ahead and pool the values, okay? And essentially what pooling does is it reduces the resolution. It basically just downsamples the image and makes it smaller, essentially. Okay? So first I've done first I've done convolution, then I've done pooling. Okay? And you'll recall what I was saying here is basically the pool gives us the features, and then each one of the squares in here, each one of these there's 9 squares here, each one of those 9 squares I'm going to use as an input into my neural network, is a way to think about it. Okay, so what I'm going to do is a thing called flatten. I'm going to take these 9 things, and I can take these 9 things and just stretch them all out to make them all, those are my 18 features now that I'm going to feed into my neural network. So they were organized as pixels where they have location information that they, certain pixels are next to certain pixels, because that's important when you run the convolutions through them. It depends which pixels are near each other. Okay? But once we've calculated our final features, we can just go ahead and flatten them out, put them in one long thing, and these are the inputs that are going to be fed into my neural network. And then I have what's called a dense layer, and it's just called dense because there's a connection between every node and every input and every node. Okay? There are some types of neural networks where not everything is connected. Okay, we're not going to go there, so don't worry about that. Okay, but here there's going to be a weight. We identified manually. We chose what the weights were because we were looking for things in certain positions. So we put these weights of 1s and 0s in there. They're multiplied by the values. They get summed together. They've got a bias, that negative 9,000. Okay, and so I have a single node here. There's a single node here that's collecting the values times the weights, and then I go ahead and put that through my activation function, and I get an output of 1. Okay? So this process is a convolutional neural network. Okay? The one difference, and this is the amazing, it's amazing that there's one change that I make here that makes all the difference in the world. And that is that the values in the convolutions, whether it's a 1 or a -1 or a -2, let's make them weights. Let's make them not necessarily weights, but let's make them parameters that gradient descent gets to choose what they are. I mean, I solved this problem. I'm looking for squares, so I want to use a Sobel x and a Sobel y, and I'm looking for the left and the right, so I choose my weights. But if it's a problem, you give the images to the neural network, you tell it what labels you want at the end, and let it pick the weights. We're already comfortable with that. We let it pick weights. Let's let it pick what's in the convolution. Let it choose. Maybe it wants to have something that gives a line of 30 degrees, or who knows, maybe it'll come up with something we never even thought of before. Let the data drive what the convolution should be. And that is amazing because now we don't have to create any features. We don't have to do any thinking. We just feed the raw image in and let it figure out the features and let it figure out the weights. Why not, right? It's amazing. And to me, this was what really got me reinvigorated to get back into machine learning, because I was so tired of, I got to find the best features, and which ones do I use, and I got to try this feature versus that feature, and do I use that? It was such a pain. I'm like, I'm doing all the hard work here, man. This is supposed to be artificial intelligence. I'm doing all the heavy lifting, okay? The AI should be doing the heavy lifting. And amazing, it is amazing what you can do with these convolutional neural networks. It absolutely shocked me. I was like, really? I couldn't believe it. And I had a strong, long background in machine learning, and to see what these things can do is absolutely incredible. Okay? All of these things, I purposely organized this in the types of layers that Keras has. Okay, we already talked about the dense layer and the activation layer, so they're not strange to you because I introduced them in the video on Wednesday. Okay, but these other ones, the flat and the pooling and the convolution, those are all Keras layers, the names of Keras layers. And this is how you're going to organize your Keras sequential model, is with all these layers, and you just put one layer after another. Okay, there's one other type of layer in Keras that is not here, called the dropout layer. I did not solve this project with the dropout layer. It's not necessary, I don't think, for this problem. And I haven't used dropout that much myself personally, but it has become very popular. And again, it's shocking in how well it works and what it does, but it is a method for preventing overfitting, so that you don't have to watch the validation set and the training set and see when they start diverging. Okay, to make sure that you're not overfitting. And what the dropout layer does, and it's amazing. There's so many really cool ideas that are coming out now, and it turns out that it works really great. And so what it does is, let's say I put a dropout in between the pooling and the flatten layer. And what you would do is you'd set a certain percentage, maybe 10 or 15 or 20%. And what it'll do is, in every forward pass, it will randomly choose that percentage of these connections and set their weights to 0. Essentially eliminate those connections. Okay? And so only the other connections get updated, but not those ones. Okay? Then the next forward pass through, it picks another random 15%. And so it randomly turns off some of these things so that the others have to pick up the slack. And essentially, if you let them all be open and always be updating, you're always pounding at all of them, and they're basically always getting fine-tuned and fine-tuned and fine-tuned to your data, and it can end up getting overfit that way. But if you're randomly pulling the plug on some of these things, the others have to have information in there to be able to carry everything through, and it's always different. Okay? So it can prevent overfitting, and it can also help make generalization better. And that's the other thing that I've absolutely blown my mind with the convolutional neural networks, is they generalize really well. Now, I think part of that is because most of the convolutional neural networks are being fed massive amounts of input data, 20,000 images, 50,000 images, and if you have that much input data, you do tend to generalize better. But it does seem to me that these convolutional neural networks generalize better than just regular multi-layer perceptrons. Okay? Now, just like multi-layer perceptrons were based on the idea of what's happening in the brain, so are the convolutional neural networks. There's neurobiologists that look at what happens in your brain and the visual cortex, and it does appear that there's something like convolutions going on, maybe not necessarily convolutions per se, but building these feature maps of taking the raw image we see and modifying it in some way so that we can pull out salient features out of there that are important for us. So there is actually a biological background for this idea of using of the visual cortex sort of doing all this pre-processing of the convolutions on the input image, and then feeding the results of that into the neurons in our brain. So there is some biological background for this. Okay. The convolutional layer is really the most important one when you're building these guys, and I wanted to show you when you're adding these convolutional layers, the different types of parameters that you can send to them. We're going to be using two-dimensional convolutional layers. If you think about an RGB image, I had a grayscale for my square, but imagine that it was an RGB and there were 3, okay? The way you would build your convolution, you would run your convolution across the R part, you'd run it across the blue part, you'd put it across the green part, and all of them would sum to a single pixel. So the R, the G, and the B would all get convolved across individually, and they all sum into there. Okay? Now, with a 3D convolution, you have your convolution and you look straight down and you go all the way through and you pull all the pieces into one number rather than looking at them all individually. So there's 2D convolutions, there's 3D convolutions. The 2D convolutions are generally more common. Okay? So we're going to be using the 2D convolutions, and you need to choose how many output feature maps do you want to have. Okay? In this case, I had 2. I had an output feature map for the X direction stuff and output feature map for the Y direction stuff. Okay? So I chose 2. I mean, you can put however many you want. Okay? Now, again, you don't choose what the values are in here. It's going to choose the values, but you choose how many there are. Okay, and the size of the kernel. Okay, so here's the kernel size. In this case, we used a 3x3 kernel, and it does seem to be appearing the consensus for whatever reason, I'm not sure, seems to be towards 3x3 kernels. They seem to be the most common. You do see some 5x5s out there too, but those are 3x3 is by far the most common. Okay.
Does that depend on how big your image is, resolution-wise?
No, it doesn't seem to. It doesn't seem to depend on that. I'm not sure, but it seems that no matter what size, you usually use the 3x3. Now, if you do have a massive resolution of your image, you may increase your kernel size. You may increase your stride to make your output be smaller. or you might just do a lot of heavy pooling or something, because if you do have a very large resolution image, it can end up taking forever to do anything, and it may not be worth it either, depending on the size of the features, the size of the things in the image you're looking for. Okay? Then there's an input parameter called border mode, same as the default. So if you didn't do anything with border mode, you get same, so it's the same size, the input and the output image. I don't know why, I wish they would call this strides. I've never seen anywhere else that calls it subsample. It's much more common to call it stride, but again, the default for this is a 1x1 stride, that it just shifts that kernel over 1 pixel at a time, both in row and column. But you can change that, and I mean, it does in a way. It is a subsample. If you have 2x2, it's gonna have half as many things, and it's gonna downsample it. So in a way, it makes sense to call it subsample. But by far, stride is the most common one. I like that one. You know, it's like the stride of how far you step when you're running or something. So I do kind of like that one. Then there's input shape. In this case, it was a 9x9 input image. Okay. Now the only layer that you have to specify, that you must specify the input shape, is the first layer. Because when you add you do sequential with nothing in the constructor, it doesn't have any idea about what you want. And when you add the first layer, you need to tell it how big is the thing you're passing in. Okay, now that could be like a 32 by 32 by 3 because it's an RGB, you know, so you can pass in RGB and pass in the whole thing, all the layers of the color space. Okay, but you need to tell it what the input size is. The next time you add a level, you don't need to tell it what the input shape is, because it already knows what the layer was before it, and it will infer the input shape from the size of the output of the previous layer. So you only need to put input shape if it's the very first layer. The others are implied. And you know, it actually might take you a fair bit of calculation. It's not obvious to go through and figure out what is the output, how many things are there in the output, what is the output shape, you know, when I do this. The result of the output shape here is going to be 9 by 9 by 2. That's the size of the output shape, because there's 2 layers that come out, and each of them happens to be 9 by 9 because I used same padding and a stride of 1. So the size of the output is going to depend on, you know, the padding and the strides and even the kernel to some extent if you don't have same and 1 by 1. Okay, so it's not always obvious to know exactly how many, what the size of the output is. That's one of my biggest pet peeves with TensorFlow, is that you have to tell every layer how big it's getting from what it had before. And it's like, well, just calculate it yourself. The information's right there. It should be automatic, but it's not in TensorFlow. So I like that about Keras. All right, so that's adding a convolutional layer. Here, I went ahead and pulled the Roomba problem. Okay, and I was like, well, let's solve the Roomba problem. Let's throw out the hog stuff and the color histogram stuff. Let's just load in the RGB image, and let's feed that RGB image straight to a convolutional neural network. So this code was too big to fit on one slide here, so I just cut out the part of the code that deals with building and training the model. But again, I did upload that so you can look at. Basically, I load in Roomba 1 data, load in Roomba 2 data, load in Roomba 3 data, and then I make this list IM be a list of Roomba 1 plus Roomba 2's data, because that's what we use to train. And then I had IM1, that's a list of just Roomba 1 stuff. IM2 is just a list of Roomba 2 stuff, and IM3 is just a list of the test stuff. Okay? So I created a sequential model. I started off defining the input shape being the size of the first element in the list, which those were what, 200 by 200 by 3, right? Okay? So this is 200 by 200 by 3. And I said I want to have 5 filters. I want to have 5 different convolutions. It gets to pick what the values in those convolutions are, but I tell it I want there to be 5. Okay, and each of those 5 convolutions is going to be a 5 by 5 kernel. Okay, so I add those convolutions, and then I add some nonlinearity in there by putting a ReLU. Okay, and the ReLU, you'll remember, any value that's less than 0 gets to be 0. Any value that's greater than 0 stays itself. So basically the ReLU just gets rid of anything that's negative I don't worry about. Okay? Then I do a max pooling layer here, and you'll notice I used all the default parameters, and the default parameters for a max pool are to have a 2x2 kernel, okay? And that will essentially make you have half the size. That every 2x2, all those four pixels get broken down into 1 pixel, okay? And the default stride is also 1. Okay, so it's a 2x2 kernel and a stride of 1, so that's going to make that image be exactly half of its size. So at the output of the max pooling, I'm going to have 100 by 100 by 5. Okay, then I do another 5 by 5 convolution, but have 10 of them. So I've got this 100 by 100 by 5. I do a 5 by 5 convolution across all of them, and then get 10 new convolutions. 10 new feature maps. Okay. Then do a ReLU again, do max pooling again. So now I got 50 by 50 images. So 50 by 50 by 10. Then I go ahead, I'm done. So I got 50 times 50 times 10 features. So where is that? Lots.
2,500, 25,000.
So there's 25,000 features now that are being flattened. So they were organized in their image space so that they can be, looked at where they are relative to other pixels. Now I'm just flattening them all out. So I got these 25,000 features. They're all going to be fed into a multi-layer perceptron. Okay, then they go into a multi-layer perceptron with 10 hidden nodes. My activation function is a ReLU. Then I have 2 output nodes, because you remember you've got sines and cosines. Okay, so there's sines and cosines for the Roomba, so those are my 2 outputs, and I'm going to go ahead and have a linear or identity output so that it can be any value from negative infinity to positive infinity. Okay, I'm going to use the Atom optimizer. Okay, that seems to be the standard. I'm going to have a loss of mean squared error. Okay, just like we had a loss of softmax when we were doing classifications, we can go ahead and use the good old, mean squared error. That's just the average one instead of sum. Sum squared error, you just divide by the total number. It's just scaled. Okay, and then I'm going to use as my metric the mean absolute error. Now, in this case, it's not going to help me very much because that's still mean absolute error of the sines and the cosines. But if I was really, really interested, I could go ahead and code my own metric. You can have your own custom metrics and have Keras use your own custom metric. If I was really slick and had lots of time, I would have gone ahead and written my own metric to go ahead and take the sines and the cosines, do the inverse tangent, and make my metric be in degrees, be a mean absolute error in degrees. So that would be really cool. And Keras allows you to do that. You can make your own metrics. Okay? So then I go ahead and I fit my model. Okay? There's my input data. The IM has both the Roomba 1 and Roomba 2. My labels are for both of them with the sines and the cosines. And I'm going to go ahead and train for 1 epoch. Okay? Because I want to keep training until I get a particular level of performance. I don't do any early stopping here, but I make sure that it goes until I get a good enough performance. And you'll notice I had it return, have it store this thing, this history in the return argument. And history is a little odd, and I haven't worked through it all myself, but it looks like it's a class or a structure. So there's hist.history. So that thing has a data member called history, and that history, as it turns out, is a dictionary, a Python dictionary, which is something I don't really cover very much. But basically, a dictionary, you access the elements in the array using keys instead of numbers. And one of the keys in that is the mean absolute error. So I can pull out the mean absolute error. I'm indexing it with square brackets, and I'm using its key of mean absolute error rather than saying, give me the 0th element. Okay? And then I'm taking the very first one. In this case, I only trained for 1 epoch, so there's only 1 value in there, but it's in a list, so I need to pull out that element. Okay? Had I trained for many epochs, I would have the mean absolute error over all of the epochs. And then I'm going to check, is that mean absolute error greater than 0.01? And if that is true, I'm going to go ahead and fit for another epoch. So I'm going to keep fitting, keep fitting, keep fitting, keep fitting until I get a mean absolute error less than 0.01. Okay? And without the metric, it's kind of hard to know exactly what that means in terms of error in degrees, but I messed around with it and I watched and I calculated them afterwards and I found that that happened to be a good value. So it's going in training. There's no early stopping here. I think you can do early stopping with Keras, but it's actually not as common with convolutional neural networks. What's much more common is that if you're worried about overfitting, you just put in dropout layers instead of doing early stopping. Okay, so if you feel like you're having problems with overfitting, you might play around with the dropout layers instead. But I did not find that. I was, without much trouble, I was able to get, like 97 or 9, no, I think it was even getting like 99% classification in the training set. And I was cheating. I had the test set and I was looking to see what I got there. You guys don't have the test set, so sorry, I was cheating there. And I was getting, like 95s, 97s, even the test set without worrying about any sort of overfitting. Okay?
Will you upload the test set so we can train on our machine?
You have the training set. I'm keeping the test set secret.
I was talking about for the last project.
Oh, right, for the last project. Yes, I do need to upload that for you. Absolutely. I forgot about that. Absolutely, I'll get that for you. Still got to. Okay. So I didn't do any early fitting. I just trained enough to get my mean absolute error down below 0.01, and then I went ahead and predicted. I predicted, model.predict, model.fit, model.predict. Isn't that nice? It's all pretty much standard, okay? Even within Keras and scikit-learn. And so then I passed Roomba 1, Roomba 2, and the test stuff. And here I got half a degree mean absolute error, and this is actually in degrees. There's a bunch of code that comes after there to calculate the degrees. So half a degree in Roomba 1, basically exactly the same in Roomba 1 and Roomba 2. It did great with both of them, and under the 5 degrees very easily, which is the requirement for the test set. Okay, so there's nothing there. I mean, you build a convolutional neural network, you train it until your error is good enough in the training set, and you're doing awesome in the test set. I mean, is that not awesome or what? It's amazing. These convolutional neural networks are absolutely incredible. It's really, really, really amazing. Okay. On this slide, I'm going to go ahead and flip over to the browser. But here's a YouTube video that talks very nice about convolutional neural networks, and it has a lot of diagrams and stuff about how all the pieces fit together. That's really, really nice. Then this guy is absolutely amazing, and that's a screenshot of it. But let me go ahead and pull out. I think I have that right here. So what this is here's my convolutional neural network, and I can draw a number. Here's the number 9. Okay? And it classified it as a 9. Okay? And so down here, here's the input. Okay? And there are 1, 2, 3, 4, 5, 6 feature maps. Okay? And so you can see this, I can go through it. It looks like, I don't know, is that 5x5 convolution down there? You see all those little lines? So each one of those lines, how bright that line is how large the weight is for that pixel. And as I sweep it across, I'm getting that pixel, this pixel right there is from that part of the image. So I sweep across and I can see, where it's getting. So this is the feature map I get there. That's the feature map I get here. So here's the 5 different feature maps that I get. Okay? And then here, this is a pooling layer. So it's a 2x2 pool, so here, the weights are exactly the same. All of them are that cyan. Each one of those little lines is a cyan because they're all the same. And it's doing the max pooling. Let's get the largest value in there. Okay? Then here's another convolutional layer. And this is the only thing I don't understand about this, okay? Is normally what would happen is that the values that you get here would be pulled from all of these 5 things. But for some reason it's only picking from 4 of them, and that's a different 4, and that's a different 4, and a different 4. And I'm not sure if they've hard-coded which ones it picks from, or if those weights happen to all get set to 0. So one thing I'm not quite certain of what's going on in this. I read the guy's paper and I couldn't find exactly what's happening. But essentially all of the things from all these 5 things should be feeding into that one there. And you'll notice that the weights for each of those maps is different. So I have different weights for each of the different pieces feeding into that one piece in there. Question, Ben?
Wait, is that 15 there? On that, the one that
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, it looks like. Or is there another one out there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So they're going from 5 to 16. I've tried to find the pattern. You know, sometimes there's 3, sometimes there's 4. It seems to shift. I haven't been able to figure out the pattern, and his paper didn't explain that, so I'm not sure what. Normally, it would pull like this one, pulls from all 5 of them. That's the way it normally does, is it should pull from all 5 of them. I'm not sure what's going on there. Then we have another pooling layer here. Okay, so we've got another pooling layer, and then here is the first, this is the first fully connected layer. So they don't show the flattened part here, but these are all of these are hidden nodes. There's 2 layers of hidden nodes. So this guy here happened to activate. That hidden node happened to activate. Okay, it's pulling enough things from all of its weights times those flattened feature values for it to trigger. Then here's another layer of hidden nodes. That guy happened to activate because it's getting enough from all of its pieces. And then we've got 10 output nodes. These are not getting very much activation. That one got enough activation. It is quite confident that it is a 9. That 9 is much brighter than any of the other things. Its second guess is a 3, but that's a pretty far distant second. Okay? So here's a convolutional neural network that, well, I mean, it's pretty bad. Here's a... It got 2 out of that. And you can look and see, so look here, this feature map here seems to be trying to get, things along a diagonal, things on like diagonal lines. This guy here seems to be getting things sort of like horizontal lines. This sort of be like things that are on the right side of stuff. So you can kind of even like peer into the brain of this convolutional neural. What is it thinking? How did it get updated? And you can see how each one of those little pieces is pulling out information from different parts of the image and then combining it together into here to get its final classification of 2. It's quite amazing. You do no feature generation or anything. It decides what the features are. It's just absolutely incredible. So, I've got a couple more minutes. There's a few things here. These convolutional neural networks, sort of the seminal original paper, came in about 1998. So it's actually, they've been around a while, okay? But they haven't gotten popular until those last 5 years or so, okay? This guy, Yann LeCun, he is basically like the godfather of AI research at Facebook. Okay, so he's like the big Facebook AI guy. And if you look, and this network down here, AlexNet, this guy Alex Krzyzewski, he's the big AI guy at Google. So it's like Google and Facebook and Microsoft, they're all like the heavy hitters, and they're all doing all this research, and all the type of stuff they're doing is going into all the technology of the things they have. So this Yann LeCun network, it's called LeNet for LeCun. And so you'll hear there's these networks, the LeNet and the AlexNet and the VGG and the GoogleNet. These are all like the benchmark neural networks. And what a lot of times people will do is they'll take LeNet, or more like AlexNet maybe, but one of these neural networks, and they'll take the bottom half of it, the feature extraction part, they'll take that and they'll throw away the fully connected layers, the dense layers, and build new ones and solve your own problem by only updating the dense layers. Because the feature maps have already decided what is important in an image. Okay? What are the important things to get out of images? That's already encoded in the stuff in the convolutional layers and the pooling layers. And then we just need a classifier that takes the features, that flattened features, and then I need a classifier to use the features that thing already is trained on. And there's ways in Keras to make it so that it doesn't change the weights in certain layers and only changes some layers' weights. And so there's a competition, an ImageNet competition, has 20,000 images over 20 classes of all sorts of stuff on the internet, you know, dogs and airplanes and computers and all sorts of stuff. And this has been like the benchmark for many years of, you know, how good can you get on this, you know, on ImageNet. Okay, and so the best neural network, you know, the best convolutional neural networks now, they do really well on ImageNet, and it's detecting all sorts. There's cars, and there's cats, and there's computers, and there's everything possible in these 20 classes. And so what's built into the feature maps is already identifies stuff, and so you can just take what already is built there and just train the dense layer only using the features that they've built, and it's turned out to be amazingly good. And you don't have to spend all the time of training 20,000 things on this gigantic convolutional neural net. All you have to train is your tens of, you know, hundreds of things on your dense layer. And you can get really good results really quickly by reusing the feature maps that were already there. Okay? So as a bit of history, this AlexNet was like, blew everything out of the water because this ImageNet, no one had done, they had like 25% or something was the best anyone could do for years. And then suddenly AlexNet comes around and drops from 25 down to 16, which was this huge change. And it like sort of opened the door that these convolutional neural networks really started breaking through. Nowadays, they're just solving this ImageNet problem down to like fractions of a percent, which is really even, we know that there's actually more than a percent or so of human error in classifying these things in there. So basically it's gotten it to be, you know, human level perception of all of these classes on the ImageNet database is where we've gotten on the state of the art now. It's quite amazing. The last thing, I probably already over time, but let me just go real quickly here. This idea of stochastic gradient descent, here's another YouTube video you can watch that can be interesting. I mean, if you've got 20,000 images, full resolution images with, you know, with RGB layers, and you're trying to load in that entire training set and put that through all of these, I mean, there can be millions of parameters to update in these neural networks. You can't even fit all the stuff in memory. Okay, so there's an idea called stochastic gradient descent, which actually you'll take your 20,000 images and you say, well, I'll take the first 100 and I'll run them through the neural network and update the weights. Then I'll randomly take another 100, put them through, randomly take another 100, and do these batches, small mini batches of randomly chosen values out of there and train. And what happens, instead of getting a nice smooth traveling down the gradient, because I know all of the images that they're all loaded at once, I sort of go jagged around. Okay, and eventually I'll get there. I mean, I can do many more updates. Even if it's jagged, I can do many more in the same amount of time it would take to do all of them at once. So I can use many and I get jagged around and jump around, but eventually I get there. Okay, and that's actually what Atom does. It does stochastic gradient descent in there. Okay, and one of the nice things is stochastic gradient descent has been shown to be somewhat better at not being stuck in local minima. Because if you're jumping around, you're not going to get stuck in some nice, smoothly following down into some local hole. And that the jumping around actually gets you to your global minima better. So it has that added benefit. But mainly, you have to do it because these data sets have gotten so big that you can't even store them all in memory, even on this giant machines. Okay? So it's really amazing. This is really cool technology. It's really state-of-the-art. It's really pushing lots of stuff is out there. And I'm really happy to be able to share this with one of the projects. I think you'll be excited about it. It's pretty cool. I mean, in the end, to take that data and make a convolutional neural network and classify it, it's not going to take you very much time to do that. It's amazing. And it doesn't even take all that much time to train it. I only trained, 10 epochs or something like that, and it didn't take all that long. I mean, it was maybe a couple hours or something, but it wasn't bad. Okay, and then so then doing this region proposal stuff is really the more complicated part of this project. And we'll see. I still haven't gotten all the details of this selective search. We'll see. That may end up being optional. We'll see. I'll make sure it works out and it's reasonable for you guys. But now you can get cracking on doing the convolutional neural network stuff, and we'll see how it goes.